The sonic boom, our greatest obstacle to supersonic flight. Can commercial aircraft exceed the speed of sound without creating the thunderous shock wave? Is it possible to reduce the sonic impact and boost aircraft performance? Find out on NASA Edge.
Yes, we're here with Peter Cohen, and Peter, your job is to actually explore technologies related to supersonic flight. Can you tell me a little bit about the research you're doing in that area?
Sure, you bet. What NASA is trying to do is put the technology in place that will enable a U.S. company to build a supersonic airliner sometime in the near future. So we're primarily working at technologies that help reduce the environmental impact of a supersonic airplane, reducing sonic boom, takeoff and landing noise, high altitude emissions. We're also working on some technologies that help improve the efficiency and reduce the weight and reduce the drag of supersonic aircraft. Our primary focus right now is on what we consider the toughest barrier to future supersonic aircraft, sonic boom.
Can you take me through how do they actually occur, why they occur, or why they're difficult to mitigate?
Yeah. The simplest answer is the sonic boom happens because the air doesn't know the plane is coming.
Sneaks up on it.
Well, when anything is traveling through the air, it's pushing the air out of the way. It's creating a pressure change. What's a pressure change? A sound, okay? So, effectively, the pressure wave in front of a subsonic airplane travels out in front of the airplane, allows the air to get ready for the fact that the airplane is coming and start to move out of its way. Airplanes flying supersonic, it's going faster than sound. So, it's going faster than its pressure wave. So, when it arrives, the pressure changes instantaneously, creates what we call a shock wave. Now those shock waves come off the nose of the airplane, the wings, the canopy, the engine inlets, and they go out in 3 dimensions. They travel out in all directions from the airplane. The ones we're most interested are ones that go down towards the ground.
Well, so that's why the cone is so important in the design, because that's the first point of contact with that pressure.
Exactly. What we're trying to do is make that initial shock wave be the right strength, and then the waves that follow it be of similar strength and position so that they don't merge when we hit the ground. Because in an ordinary supersonic airplane, as those waves travel towards the ground, they merge. And so at a very short distance from the airplane, actually, you were left with an acoustic phenomena of 2 loud pressure impulses, that bang bang sound. And that occurs under the entire flight path of the airplane. A lot of people mistakenly think that a sonic boom is the sound of the airplane breaking the sound barrier. Well, it doesn't actually start until you get to above Mach 1. And then when you're cruising along, all under the flight path of the airplane, to a distance of about 25 miles on either side of the flight path, is affected by the sonic boom. That's why it's such a problem. That's why you really have to reduce it, because so many people would be affected by this loud sound if you tried to fly, say, an F-18 or a Concorde across the country. So one of the most important things to figure out in the sonic boom research is how quiet is quiet enough. So we have done research using simulators, basically large speaker arrays, and we've given people a variety of sounds to listen to and say, is this sound acceptable? What's annoying about this sound, etc. But the original simulator is just a little cement block booth with a chair in it and a wall of speakers on the door. We have a bigger one now, but it's not really an environment that's typical to what people experience every day. So we're always looking for ways to make the experience more realistic. Well, we found out something really interesting about sonic boom is that the further it travels, the atmosphere affects it so that even a normal boom, if you can make it travel far enough, it starts to sound like one of our idealized shape boom waveforms. So what we found is if we dive the F-18 almost straight down, just about Mach 1, it produces a sonic boom that comes off the top of the airplane, which is a weaker set of shock waves, and then travels a very long distance before it reaches the ground. And we also found that we can control the amount of sound that's hit at a certain location by controlling the dive point of the airplane, where the pilot starts his dive.
Whose idea was that to make the plane dive to do this research?
A researcher out at NASA Dryden by the name of Ed Herring, who's made a lot of contributions to sonic boom, when Spaceship One was flying, he went up and measured the sonic boom. And when he saw the characteristics of that boom, he said, boy, we could use something like this in our research. So his first thought was, well, we'll use a sounding rocket. You know, that comes almost straight down. That's a pretty good idea, because then we thought, well, that sounding rocket's going to go right into the community that we'll want to listen to. So that's probably not such a good idea. So within a few weeks, he had come up with the idea of diving the airplane. And then the idea was to create a maneuver that was repeatable, in other words, fairly easy for the pilot to do, but would produce the characteristics that we did. So we tried that a number of times. We worked on it in the desert. Since then, we've done research with it. We've actually primarily used the Edwards Air Force Base housing community as our research subjects. You know, they have to be there anyway. But it's also under the supersonic flight corridor out at NASA Dryden. But we've done experiments that tested people's reactions to sonic booms, tested structures' reactions to sonic booms, and actually tested the procedures that we might use if we were going to do a test somewhere else and try and judge reaction to sonic boom. It's really become a key element of our research to be able to produce these simulated low sonic booms using the F-18. But ultimately, I mean, we have to get off the range, so to speak. We have to get out over an average community that does not hear sonic booms on a regular basis, and their livelihood is not related to supersonic flight. So what we need is a demonstrator, is an airplane that's small and relatively affordable, but still produces that desired shape sonic boom characteristic. And we can go out and fly it over any community and have our microphones and stuff like that on the ground and begin to develop the data that says these booms are acceptable. And then we turn it over to the regulators and say, you know, please make us a law that says supersonic flight is allowable over land.
Now, is that demonstrator plane what you're developing in the wind tunnel, or what other research are you doing in the wind tunnel?
At the moment, one of our key, most recent successes was we looked at the design of a small low-boom airliner. Based on those designs, we created some wind tunnel models and verified that our design tools enable us to produce a design that meets our low-boom target. So we're fairly confident we can do this now. We need to demonstrate it in a realistic atmosphere. So our work has been focused on an actual potential product airplane. Now, in order to do kind of the final verification, we'd like to get an opportunity in the future to do a flight demonstration.
And is that a unique aircraft that you've created for that demonstration?
Well, we haven't created it yet, but it would be a unique airplane. Again, shape is king and paramount. So we'd probably use an existing engine, maybe existing landing gear from a current aircraft, but the shape would basically have to be a new design shape.
And if successful, you could go on to produce planes that would fly commercially, possibly, with low sonic booms, meaning I could get to Los Angeles for lunch and
back home for dinner.
If luggage and everything else wasn't an issue.
That technology still needs to be worked.
Awesome. Well, I was looking at some of the images in the wind tunnel, and it looks like the plane looks very similar to Firefox that Clint Eastwood flew in the movie back in the 80s. Did you guys borrow from that technology, or? Not really, no, but it is kind of interesting that the airplane is not really all that different from other supersonic aircraft designs, in that it still has a delta wing and supersonic inlets. The key thing that we're really going after is the detailed three-dimensional shape of the airplane, particularly the shape of the nose and particularly how the engine is integrated. It turns out, though, that if you're trying to create a balanced design, you're best off flying at the altitude and Mach number that match the performance of your engine and give you the best overall efficiency, and then set your sonic boom target based on that. So we're pretty much going to fly at the same altitude as the Concorde, 50,000 feet or so. One thing that's a little bit different is we're targeting a lower Mach number. Concorde flew at Mach 2, twice the speed of sound. These future airplanes will be slightly slower, maybe Mach 1.6 to Mach 1.8. And there's several reasons for that. One is the shape sonic boom solution is easier to achieve in a practical design at those lower Mach numbers, but then there's also things like the noise performance. We can make a better engine for takeoff and landing noise by flying at Mach 1.8 than we can at Mach 2. Not many people are going to quibble over 1.6 and over 2, I think, in the long run, because of the increased efficiency. I think in the long run, if you're reducing your cruise flight time by nearly a factor of 2, that's going to be a benefit worth going for.
But our goal in reducing sonic boom is to change the law. The U.S. law currently says you shall not fly greater than Mach 1 over the U.S. unless you have a permit from the FAA. We would like to replace that with you shall not produce a sonic boom louder than X dB as you fly over land. That's primarily the goal of our current research.
I'd like to work something in that law that means I can get an aisle seat no matter when I fly, if I could.
Now you're really asking for some tough stuff.